I'm Premlata, the team leader of Team MiniMax, committed to addressing the pressing challenge outlined in problem statement number 1313. Our primary objective is to develop a comprehensive solution for preventing the underloading and overloading of coal within train wagons. Here it comes under the theme of transportation and logistics and under the Ministry of Coal. Within this video presentation, we will provide an in-depth exploration of our innovative approach to addressing this critical issue. Join us on this journey as we share our strategic insights to make a meaningful impact on this important concern. And we'll go with the problem statement explanation.
The chosen problem statement title is Implementing an IoT Device System to Mitigate Underloading and Overloading of Railway Wagons. CIL has been using railway sidings to supply coal to its customers, with the loading of railway wagons at these sidings being carried out through contractual arrangements with payloader operators. However, this approach often results in the problem of either overload or underloading the railway wagons. In cases of penal overloading, any associated fines imposed by the railway are the responsibility of the purchaser. On the other hand, when wagons are underloaded, HIL covers the cost by adjusting idle freight credits in the coal bills. In the financial year 2021 to 22, the expenses incurred due to underloading amounted to approximately rupee 593 crores, whereas the cost of the wagon loading contract itself was only rupees 276 crores. As a result, there is a need for a digital solution such as sensors or IoT technology to address the challenges of preventing both underloading and overloading of railway wagons. This issue has a direct impact on economic growth and results in revenue losses, as evident from the fact that the expenses associated with underloading surpass the contracted expenses. Additionally, it has indirect implications for efficiencies since overloading demands more energy for transportation and leads to heightened wear and tear on the train wagons. The primary causes of this problem include the absence of a proper weighing system, improper weighing practices, reliance on traditional loading methods, inaccurate documentation, the pressure to maximize cargo loads, a lack of updates and regulatory guidelines, and the variability of cargo. Our approach to overcoming this challenge involves the implementation of precise weighing systems. These systems will be strategically placed at regular intervals along the railway tracks and at the coal loading unloading sites. Subsequently, we will provide real time data sharing with both our suppliers and customers to ensure accurate and efficient coal transportation. Now here we go with the demo. In this small scale demonstration, we've created a prototype to measure and display weight using various components. The key components included a Node MCU HX711, an analog to digital converter, and a LCD display. The core element is the load cell capable of measuring up to 40K. To make it work, we first upload a source code to the Node MCU. Once the source code is successfully uploaded to the Node MCU, the system can accurately measure weight and show the results on the display. Let's explore the source code that was our weight detection prototype. So this is one of the source code, but this is only used to find the calibration factor. The first few lines are necessary library, which needs to include it before we write the code. Next, the setup blocks contains the instructions which need to be followed before weighing, and also the setup block contains the code for connection of the LCD. Now the final one loop block is main one, which prints the measured weigh with 3 decimal points, and the if block provided for the adjustment of calibration factor, as we already seen in the setup block instructions. The ASDF keys contribute for the increment and ZXCVO keys for decrements by 10, 100, 1000, 10,000. As seen in the calibration code, the first few lines are for the library including. The setup block also contains the code as in the calibration code, but the difference is the instructions that are not present in the loop block also. The calibration adjusting if block is not present in it. So this is the main source code that needs to be uploaded. Now we will go for video demo of how our simple prototype works. First, we need to determine the calibration factor and update it in our code. Before that, it's essential to verify the code. After that, we need to upload the code, but I already uploaded here. To proceed, you can simply open the CAL monitor. In the readings, you will observe some repeated values along with a calibration factor. In this step, we should copy this calibration factor and paste it into our code. Now here we go with the demo. Now that the small scale demo is over, let's look at the real-time implementation of the solution. For this challenge, the first step is to install the sensors in the truck as shown in the video. Next, we need to detect the crossing of the train detection in order to determine the weight of the wagon. The next step is to detect the weight of the wagons and classify the load as overloaded or underloaded and notify both the seller and the buyer. Finally, we need to transfer the data to a server or cloud so that the purchaser and seller can access it in real time. Additionally, we will store the data for analysis. To prevent theft and take necessary precautions, the setup will be placed at regular intervals or junctions, as well as at loading and unloading stations. This will reduce the theft and will give you insight about where the loss happened.